As we watch the video of the experiment, focus on a few specific camera views. There are a pair of cameras just inside the front door looking toward the area of origin. One is a video camera and one is a thermal imaging camera. We have another pair of cameras in the dining room that are focused on the wall approximately 3 feet to the left of the point of origin. You can see the front side of the structure. Notice that all the exterior openings are closed. The same is true at the rear of the structure. You can see that the fire is building. In the thermal imaging view, we see evidence of the ceiling jet moving across the room, and we see a well-defined thermal plume. Notice the foam plastics in the furniture melting, dripping, and dropping some of the fire down to the floor. You can see that our smoke layer is building, and we start to see some leakage through the cracks in the doorway and some leakage around the window. At around 3 minutes, the fire will start to transition to flashover, and you're going to see the heat spread throughout the living room pretty dramatically. We are going to see evidence of the pressure building up in the living room by the jet flames that have pushed out of our window plug to allow some pressure relief. As soon as these hot gases hit fresh oxygen, they burn. As the hot gas layer fills the living room, we see smoke pushed out under the bottom gap of the front door. At that point, the fire had reduced the oxygen below 15% in the space and could not continue to burn. The temperatures drop, the heat release rate drops, and the pressure inside the building decreases. So now the building is drawing air in around the cracks and trying to get more oxygen in for combustion, but it can't pull it in fast enough to keep the fire going. The fire apparently has consumed most of the oxygen in the space, or at least the oxygen that it needs to continue flaming combustion, so the temperatures drop. We have some sense of pressure in the living room. It surprised us as it overran the sensors we had in place. But then the interesting thing is that after the push, after you saw the jet flames coming out the window, the pressure dropped below zero. The low pressure in the building allowed a little bit of air to be drawn into the building, which enabled the fire to burn a little bit more. And then it went out for the final time, and the pressure slowly equalized. What about oxygen concentration? In this graph, we have oxygen concentrations that were measured at 4 feet above the floor. We can see that as the hot gas layer comes down, the sensor by the kitchen starts to come down first, and then by the front door, and then the living room positions on either side of the sofa. As the fire begins to decay, we see the oxygen concentration drop below 15% on the hallway side of the living room. This bottoms out around 10%, while the others continue to decrease. As the pressure changes and air is being drawn back into the compartment, we can see that the concentrations slowly increase. Now let's take another look at this scenario. This fire room has significantly more fire damage than the previous case. Looking at the wall with the window and the door, we can see that the wood molding around the window has been charred. In some areas around the window, clean gypsum board is evident. This evidence indicates that sections of the charred wood molding fell away after suppression. The wall has thermal damage across its width from the ceiling down to the floor. The area under the window's right side has burned through the paint and paper to expose the gypsum. The door's surface has soot deposition, and some of the soot has washed away with water during suppression. However, there is a line of demarcation between the soot and the clean area near the bottom of the door. Thermal damage also extends across the wall adjacent to the doorway. The ceiling and floor have been burned. A piece of furniture protected the section of the carpeting. There is a section of the wall that has a heavier deposit of soot on it. This aligns with the protected area on the floor. This is similar to the previous case, except the lines on the wall are not as clear as before. This means hot gas flowing over the wall transferred thermal energy to the wall via convection, and this had a role in generating the damage. The wood floor in front of the doorway is charred. Examine the wall to the right of the doorway to the kitchen. On the wall area to the right of the doorway, the thermal damage is nearly uniform from approximately 30 inches above the floor to the ceiling. The fourth wall has a distinctive line of demarcation between a clean burn area extending from about 3 feet above the floor to the ceiling and the remaining thermally damaged areas of the wall. The floor has charred areas extending from the wall out toward the center of the room. Although the carpet and padding have burned through to the subfloor over most of the floor area, there are still areas that have been protected. The ceiling has sustained significantly more damage than in the previous case. Notice the cracking of the gypsum board along the ceiling. As we look at the room with the remains of the furniture, all of the upholstery and foam padding are consumed, and the wood-based components of the sofas and chairs are charred on all sides. The clean burned area below the window's right side aligns with the chair that was closest to the door. The floor in front burned, as did the wood cabinet supporting the television. The carpet and padding had not burned through to the subfloor from the front of the sofa to the wall with the kitchen door. When compared to the fire where all the doors and windows were closed, this fire burned for a longer duration and had a greater spread throughout the compartment due to a supply of oxygen coming through the front door throughout the fire. Post-flashover, the impact of the oxygen was limited to areas between the area of origin and the source of the oxygen, in this case the open front door. The clean area on the wall near the area of origin was generated pre-flashover. The fire damage that occurred closer to the door and the clean burn area behind the chair closest to the door happened post-flashover. Let's watch the video. As you can see, the front door is open from the start of the fire. The first 2 minutes and 30 seconds are very similar to the first fire, so we're giving ourselves a little head start here. As you remember, the transition of flashover started a little after 3 minutes in the first experiment, and it began to shut itself down at approximately 3 minutes and 30 seconds. Here we're getting a similar transition of flashover, but we're going to see something slightly different. We have flames coming out of the room, but what do you notice at the location near the area of origin? There's no burning, and the temperatures are dropping because the seat of the fire is moving from the area of origin on the sofa toward the source of the oxygen by the front door. We're going to see some changes occur at the front door as the fire cycles. Notice that the gas is coming out of the front door and it's looking pretty sooty, indicating that we're not burning all of the fuel. We have some unburned fuel leaving the room as the seat of the fire basically moves to the wood floor in the foyer or the entryway to the front door. Most of the burning is going to be taking place right at the doorway, and we're going to effectively lose our neutral plane or any airflow back into the living room, and the living room temperatures will continue to decrease. Notice how clean it's burning at the front door right now. That's because most of the burning and most of the fuel is very localized to the doorway as we start to char and burn the wood flooring. Now we're going to change that flow. The burning rate of the wood floor will decrease, which is then going to allow more oxygen to penetrate a little deeper into the living room. And then we'll notice that we're going to start to heat up the space a little more. Don't mind the firefighter there. He's just doing a bit of touch-up to protect some equipment. So we start to see that we're really getting cool air again deeper into the space, which will allow some of that material to rekindle and burn again. We're about 3 minutes post flashover right now. You can see that we've got a definitive neutral plane at the door once again, and now the temperature in the living room is increasing. We can see that we're starting to get more heat back toward the area of origin, which is deeper in the space remote from the front door. We're not going to take a very aggressive firefighting attack. We're not going to do a very aggressive mop-up like you would typically have in the real world. We want to see that in the best case what these fire patterns would look like. We're about 4.5 minutes post flashover. The fire seems to reach sort of a new steady state, and before we start to drop gypsum board off the ceiling or the walls, we wanted to address the fire. We're going to use a very light stream, and you can see evidence of the hose stream going in and the cooling that it's providing. So again, nothing terribly dramatic, and within 30 seconds or so, we'll get the fire knocked down pretty quickly. Let's look at the data. We see the hot gas layering with the thermocouples started near the ceiling and then worked down to about a foot above the floor. We transitioned through flashover and temperatures increased to well over 1100 degrees, our flashover threshold. The fire enters a decay state due to a lack of oxygen. This is when the seat of the fire begins to move toward the doorway, and here's where we lose our neutral plane. Basically, we have that clean burn going on right at the doorway, and then when the fire slowly builds up again, it reaches a new normal. We see that the pressure with the door open at the start of the fire is much lower. But the important thing to note is that the pressure near the ceiling is higher than atmospheric, it's positive, and as we get lower toward the floor, the pressure drops. The negative pressure is what allows for convective heat circulation or flow within the space. You can see that the oxygen concentration is below 15% everywhere except by the front door. And here we see that an inexpensive hollow core door can block heat and isolate a bedroom from being part of the flow path. In the closed structure experiments, the living room fires were ignited, flashed over, and self-extinguished in less than 5 minutes. The post-flashover burn time was 30 seconds or less due to oxygen depletion. In the living room fires with the front door open, the supply of oxygenated fresh air allowed the fires to continue to burn until they became fuel depleted. These fires were extinguished by a hose stream before running out of fuel. The time from ignition to the start of suppression was approximately 10 minutes. Both experiments burned for approximately 7 minutes post-flashover. Here we see the post-fire suppression photographs of the living rooms that burned with no open exterior vents and the ones with the front door open. The difference in the extent of fire damage is apparent. The open door provided an exhaust vent for oxygen-depleted combustion products and an intake vent for air. The continued supply of air supported combustion for a more extended period. During that time, the combustion zone moved from the area of origin toward the open front door, and then later in the experiment, the fire began to move back toward the area of origin. When the combustion moved toward the front door in the open door experiments, the TV stand was ignited. The difference in the fire patterns created on the wall near the front door depended on whether the front door was open or closed. Let's take a look at the next series of experiments conducted in the two-story colonial test structure. This is the basic floor plan of the colonial test structure. Click to see the instrumentation diagram for the two-story structure. Let's take a look at this scenario. As we look around this fire room, sharp lines of demarcation between fire-damaged areas and areas with no thermal damage are visible on the wall behind the sofa. A clean burn area is above the area of the sofa near the point of ignition. Convection flows generated this fire damage. As we look up the wall, the thermal damage from the fire and the hot smoke plume is aligned with the sofa. After the plume impacted the ceiling, the hot gases turned and spread across the ceiling, resulting in paint and paper burning off of the gypsum board. The thermal damage on the ceiling decreased as the distance from the ignition sofa increased. The wall on the rear of the house shows thermal damage adjacent to the ignition sofa. The damage to the chairs appears to be due mostly to radiant heat transfer. As we look up the wall, there is evidence of a second plume aligned with the chair closest to the ignition sofa. This evidence would indicate the chair was supporting flaming combustion at some point during the fire. There is no thermal damage to the wall above the chair, remote from the ignition sofa. Looking down at the floor of the fire room, much like the ceiling, the thermal damage to the carpet and padding decreased as the distance away from the ignition sofa increased. On the left, there's no thermal damage to the counter or cabinet. Only the plastic case of the flat-screen television started to melt from the heat. Looking toward the front door, the line of demarcation on the carpet is visible. Note the unburned fabric on the side of the second sofa, which is remote from the ignition sofa. On the walls adjacent to the foyer, no thermal damage is present, only soot deposition. There is no visible line of demarcation indicating an intake from the front door because the door and all vents were closed for the duration of this fire. In this scenario, all of the exterior windows and doors are closed. As we watch, you can see that smoke is collecting on the ceiling of the second floor and then filling the gap in the hallway and moving across to the open stairs. Notice the fire's burning under the sofa first instead of spreading across the seat. Temperatures are increasing on the second floor, and we see the fire begin to transition to flashover. You can hear the pressure pushing around the door. You can see the smoke layer come down as it is leaking around the edges of the door, and then the fire shuts itself down. We see a nice pattern for our area of origin. A second plume came out from under the sofa and unburned areas there. Like previous experiments, the temperatures go up and down very quickly. The pressure as the temperature increases is positive and reaches the limits of our meter, and then as the temperatures decrease, the pressures also decrease. Looking at the data from our oxygen sensors, we see that they start out at ambient conditions, about 21%, and then as the heat release rate of the fire increases and the temperatures go up, the level of oxygen within the structure goes down. The levels of the oxygen drop below 15% and couldn't provide enough oxygen to sustain flaming combustion. Now let's take a look at this scenario. Walking to the fire area and scanning the walls of the two-story family room, it is evident that one corner of the room has more damage to the walls than the other sections of this area. Looking up, we observe that the paint and paper on the ceiling and upper area of the family room walls are burned off. The area above the corner has more damage than the rest of the ceiling, as evidenced by the burned away spackling and cracks to the gypsum board. If we look at the floor, there is a distinct demarcation line along the wall and corner where the carpet and padding are burned away. The plywood subfloor is charred, while there is an area along the wall where the carpet, padding, and subfloor have not been burned away. The clean circle on the carpeting represents a protected area from an object that was present during the fire. At the front door, paint and paper are burned off of the gypsum board wall on the upper level. However, on the lower level of the house's front portion, the fire damage is limited to soot deposition. This damage indicates that the walls on the lower level were cool enough for soot from the smoke to condense and deposit on the walls. In the foyer, the line of demarcation between the fresh air intake and the soot deposition is visible on the walls. This is the result of a supply of combustion air for the fire room. Turning 180 degrees toward the back wall, it is visible that the wood molding around the window to the right has partially burned away, while the remaining portions are just charred. The wood molding around the window on the left is mostly intact, except for the lower right-hand corner. Below the left window, distinct demarcation lines are visible on the wall, baseboard, and carpeting. The counter has soot deposition on the left side of the counter. On the floor in front of the counter's soot-covered section, the carpeting and subfloor were protected. The carpeting in front of the clean portion of the counter is covered with ash. As we return to the wall with the most fire damage, there is a vertical line of demarcation between the burned and the unburned portions of the wall on the first floor. To the left of the line of demarcation is a clean burn area. Based on what you have observed, answer the following questions. These experiments have demonstrated that increased ventilation resulted in additional burn time, additional fire growth, and increased fire damage. Fire patterns within the room of origin led to an area of origin when considering the impact of ventilation. Fire patterns generated pre-flashover persisted post-flashover if the intake ventilation points were remote, and the location of the ventilation relative to the origin of the fire changed the location and extent of the fire damage.